Afternoon, let's enjoy Allan Sly's talk.
Thank you. Okay. So to finish off, I'll talk about given what we've built up over the last couple of lectures, how to get thresholds for a couple of different models, for the largest independent sets of random regular graphs, and then for the in the less homogeneous sort of setting of random k-sat. So the biggest independent set isn't really a spin system, but you could think of it as in terms of the hardcore model, which is just independent sets on your graph weighted according to lambda to the power of their size. And so if you set lambda going to infinity, you'll put most of the mass on the biggest independent sets. So we'll sort of take that view of things. And so what would the belief propagation equations look like? Well, this would be the formula. And so what do you get when you take lambda goes to infinity of this recursion? Well, essentially, if any of the inputs are 1, you'll just get 0, and otherwise you'll get a 1. So this will be the now a simpler recursion we can we'll have. There'll only be 2 values for the messages, either 0 or 1. And if you have if all the incoming messages are 0, then the outgoing message will be 1. But if you have 1 or more 1s, then the outgoing message will be 0. And so I'll call these sort of warning propagation messages. And so the basic object we'll look at will be configurations of these. So on every directed edge of the graph, you either have a 0 or 1. And just following this rule that if there's no incoming 1s, you get a 1. If there's 1 or more incoming 1s, you get a 0. So in this case, if these were the sort of messages coming from the leaves, you could do the recursion. This would be the only 1 you get because it has all incoming 0s. And then these would be the sort of downward facing messages. Okay. So how do we relate that to a sort of an independent set? Well, these messages are what the messages are trying to say is a 1 means the vertex wants to be a 1, a 0 means the vertex wants to be a 0. So we could call so a vertex that has at least 2 incoming 1s, we'll call that a type 0 vertex, and that's definitely not going to be in the maximal independent set. A vertex that has no incoming 1s, so none of its neighbors want to be a 1, you could make that a 1 in your maximal independent set if none of its neighbors want to be a 1. The sort of boundary case is when you have exactly 1 incoming 1, and then the rule would say, so this message would be a 1. But the other incoming messages are 0, so the outgoing message on that edge is also a 1. So you have an edge with a pair of 1s going across it. And we call these vertices free vertices, and they come in pairs. They're just the edges where you have two 1s on the 2 directed edges. And essentially what it comes down to is
the message you pass from top to bottom or from bottom to top?
the messages are on, so you have directed edges, so you have 2 messages on each edge. Yeah. And the free ones are when both of the messages on that edge are a 1. So it means that both of these vertices would like to be a 1, but because it's an independent set, only one of them can be, so you have to pick. So the total number of the biggest independent set that you could sort of construct in this way would be, well, you take all of the type 1 vertices and half of the free vertices. For each of these edges where you have a 1, 2 1s on it, you pick one of the endpoints. Okay. So this is, and essentially, at least in the regime we'll be looking at, these free variables will be kind of rare, and there'll be sort of essentially form very subcritical trees. So so you will be able to sort of choose set exactly half of the variables to be free and still have an independent set of this size. Okay, and we can think of, if we knew the empirical distribution of these configurations, the proportion of how many edges there were with zeros and ones and so on, then we could write this as sort of the empirical distribution in a product with something which just times the number of vertices, and so this will be a function of the empirical distribution. Just what I want to say. Okay, and so then we want to count these configurations, work out the expected number of them, and we said last time how we do that. So for a particular empirical distribution H, we can work out the exponent for how many configurations we expect, the expected number of configurations with that size. But now we want to do a sort of constrained optimization, looking at these warning propagation clusters, but just the ones that give us a sort of independent set of density alpha. So now, so we said if we were just doing this unconstrained optimization, then we can just sort of solve the belief propagation equations. Fixed points of that will give us, will correspond to the maxima of that, and then, okay, but in this case we have a constrained optimization problem. So what do you do with constrained optimization problems? Well, one thing you can do is just introduce a Lagrange multiplier. So we'd look at this minus some Lagrange multiplier theta times h in a product psi, and then just plugging in the formula we had for phi, it would look the same, except rather than h in a product psi, which was the weight, we'll get psi plus theta. So actually, this is just a different spin system with a slightly modified weight. So the idea is we now look at a family of spin systems with different weights. So the weights are just, you look at theta to the power of the number of of the size of the independent set you get, which is basically exactly what you do in the hardcore model. That's where we would have had lambda to the size of the independent set, and then we want to choose a value of theta such that the maximizer of this has density alpha. Okay, so we have a new spin system. We can write down the belief propagation equations for this one. So if Q is the density of ones, it's just this formula. So this is and so we want to solve this fixed point equation, and the solution that you get will be a function of theta, this weight. Okay, and then and there's just a unique solution to this. So it's the unique maximizer. So this will be the one that gives you the biggest contribution to the free energy. So it'll tell you the empirical distribution that gives you the biggest contribution to the free energy for this sort of weighted warning propagation model. Okay, so and then you can just, we have a formula for phi, we can just sort of plug it in, and then this term is subtracting off the weight of a typical solution. So this will just tell you what is the number of warning propagation configurations that or the expected number, or the normalized log expected number when we use this weight theta, and the size will be this one. And so what we want to do is just take the biggest value of theta such that this is non-negative. So the largest, so we have these warning propagation equations. We weight them according to theta. Having a bigger value of theta puts more weight on the ones that give you bigger independent sets. And you just take the biggest value of theta such that you still expect to see more than one on average configurations of that size. And then the one RSB prediction is just you choose the optimal theta and then you look at the size of the independent set corresponding to that theta. Okay. But this is so far just a first moment calculation. So we need to show that we actually do have solutions like this. And so, okay, so suppose theta star and q star were the fixed points that we just found. We can now do the second moment, count pairs of warning propagation equations. And so now, if we're looking at pairs of these configurations, that means each edge has a pair of either zeros or ones. So it's either 0, 0, 0, 1, 1, 0, or 1, 1. So the BP fixed points will be in terms of a distribution over those four values. And essentially you can write down the set of equations, work out the fixed points of that, and at least when d is large, you only get two. One corresponds to just the two copies being completely independent, and the corresponding weight is the original weight. The other corresponds to having two sets of messages that are completely identical with each other. And for that you need to weight them with sort of square root of the weight from the first moment, just because you get that weight for each copy. I was sort of confused at first why you have to look at these with different weights, but essentially what we're doing here is doing some constrained optimization problem. There's two maxima in the set of constraints that we're looking at, and these are just the two different Lagrange multipliers that correspond to the different maxima, and so in general they will be different. So if you put all that together, at least so when d is large enough, whenever the number of warning propagation equations has a sort of positive exponential rate of growth, then the second moment method works, and that tells you that there are sort of a reasonable sort of alpha many or order alpha n independent sets of that size. And the size of the maximal independent set is concentrated by the Azuma-Hopting inequality. So this is at least a lower bound on the number of independent sets. And you can use the interpolation method from yesterday to prove the right upper bound. And if you do this in sort of more detail, you can get sort of a finer information. So what I've told you predicts sort of alpha star the density of the largest independent set, but actually there's a logarithmic correction, and after that you get fluctuations which are just order 1. We don't know what the sort of distribution of the remainder is, but I think the right guess is probably some randomly shifted discrete Gumbel distribution. But well, if you're just working with the first couple of moments, it's not clear how you can sort of hope to pin down the sort of distribution at that level. And you could say, well, maybe you could work out higher moments, but actually it seems like if for any fixed d, if you worked out not just the second moment but sort of higher moments, at some point they'll sort of blow up, and you won't get the right sort of convergence there. Okay, so that's maximal independent sets. The fact that the graphs we were doing this on were regular was really important. Things become more complicated if the underlying graph is not regular, has a so I'll tell you about what happens in the random k-sat model. So just to remind you, the random Boolean formula, n Boolean variables that are either true or false, which I'll label as either plus or minus, and the constraints are you take choose k of the variables or their negations and take the or of that, and that's one constraint, and then you take the and of alpha n of these. Okay, so that gives you a random Boolean formula, and we want to know, is it satisfiable? Okay, and we can think of this as being on a hypergraph where for each variable is a vertex, and each of the clauses is also a vertex, and we just so these are the clauses, these are the variables, and we just connect a variable to a clause if the variable appears in the clause. So we get some sort of random bipartite graph. Okay. So when I talk about the graph, that's the graph I have in mind. Okay. Now it's easy to work out the expected number of solutions because essentially each of the clauses is satisfied or is unsatisfied with probability 2 to the minus k, and they're chosen independently. But this is an overestimate for every sort of clause density alpha. So this is never the right sort of formula for the typical value of z. And what goes, which is not good if we want to use like the first and second moment method. It can never work in the most simple form just applied to the number of solutions. So what goes wrong? Well, think about what the marginal of the variable is. So the probability that it's a half. So if we'll have some variables that are in none of the clauses, and so they're of course equally likely to be true and false. But even if a variable is just in a single isolated clause, its probability of being plus, the marginal, will be either 4/7 or 3/7, depending on whether or not that variable was negated in the formula. Okay, and when ones are in more sort of complicated sets of components, you get more complicated marginals as well. So the marginals will vary over the vertices, and this will happen even when you only have a sort of very, very sparse number of clauses. So why is that a problem? Well, okay, let's look at the effect of what happens when we add in one extra clause. So A will be a clause connecting k of the variables, and the signs will say whether or not they're negated or not. And then the ratio of the old partition or the new partition function when we add in an extra clause divided by the old partition function is just the probability that a random solution under the old one satisfies this clause, which we can just write out like this. If the m's are, and since the m's vary, this the right-hand side will vary. So adding in a new clause will have a multiplicative effect on the total number of solutions. I mean, it will decrease it by some multiplicative amount, and by a random multiplicative amount. Okay, and so if we just wrote the total number of solutions as a telescoping product, you can think of this as a product of these ratios, which are random variables. I mean, they're not independent, but they're, you can think of them as more or less independent because we're adding in independent clauses. And just products of independent random variables don't tend to be concentrated, except unless the random variables are just constants. So if when you add in a new clause, it has some sort of variable effect on how much it decreases the partition function by, that's bad news if you're looking at the moments. So in some sense, we want to kind of do this, but condition on the marginals in some way. So we have to be able to deal with the fact that different variables have different marginal probabilities, and that's maybe the main thing that we need to grapple with. Okay. So what is the distribution of the marginals? Well, we can sort of heuristically work out what that should be by saying, well, okay, so if we look at all the vertices in the graph, there's some empirical distribution over those marginals, and if you have n vertices and n plus 1 vertices, that shouldn't really be any different, and it shouldn't really be different if you have 2n vertices either. So imagine that this root is just a new vertex that we added in with a Poisson number of sort of clauses connected to sort of independently chosen variables in the formula. Okay. So we could work out the marginal at the new vertex, the probability that it's a plus, based on the sort of previous marginals in these leaf vertices, if we could assume that they're independent, which is sort of expected to be the case if it's in the replica symmetric phase, not sort of really close to the satisfiability threshold, but at least when you have a low density of clauses, this would be true. Okay, but now the distribution of the marginal at the new vertex should be, on average the same as the marginals as the empirical distribution. So it should satisfy. So some fixed point equation should be satisfied that if we picked these leaf ones that were independently according to the empirical distribution, that when we add in new clauses and a new variable, that one will also be distributed according to our guess for the empirical distribution, which I'll call mu. And so the fixed point equation is just this measure valued recursion, which is just sort of essentially saying, you do this at random. So d and d plus would be the number of edges that the variable is in. D plus is the number where it's not negated. D minus is the number where it is negated. Those will be approximately Poisson, and then these terms would correspond to the effect from each of the clauses. Okay. Okay, and well, you can show that such a fixed point equation, or that there is a mu that satisfies this fixed point equation. Okay, so suppose we believe this heuristic and said that okay, that measure is going to be the empirical distribution of the marginals of the vertices. What is the right guess for how many solutions there are? Well, the heuristic could be, okay, you go from a graph with n variables to n plus 1. This would be how much the partition function changes, or like the log partition function changes when you add in a new variable. then we need to subtract off something because we'll remove some number of clauses as well, just because the probability that any one clause is in the formula decreases as you increase n. And so this is the replica symmetric prediction, and it's strictly less than what you expect for than the normalized log expected value. And so this is expected to hold for the replica symmetric phase up to the condensation threshold. But of course, we still have to grapple with the fact that there's clustering of solutions as well. Oh, actually, I wanted to say that, I said it's expected to hold. I don't think so. So this is not proved. It's maybe not so hard to prove if alpha was really small, but for the range of interesting alpha, even showing this in what should be the easy phase is still an open problem. Okay, so the 1 RSB prediction is that we should, is really a story saying that you should look at clusters of solutions, not just the solutions themselves. And I said, we can think about clusters in terms of belief propagation and messages, which will be a message from a vertex saying, what's the probability that I'm plus? And you could imagine that some of the time that probability is 1, some of the time the probability is 0, and some of the time it's somewhere in between. And so what we're going to do is just simplify the analysis to saying that, well, there's actually only going to be those 3 possibilities, 1, 0, and in between. Or another way of sort of saying that will be, for each of the variables, we're going to say that they can a cluster will be defined so that they have 3 possible states. Either they're a plus or a minus, or they're a free variable. And the way you should think about this is that within a cluster of solutions, the variables labeled a plus are always plus, the variables labeled a minus are always minus, and the variables labeled with as free can be both with some probability. And we're not going to think about what the probability is, just that it's somewhere between 0 and 1. Okay, and so then the rule will be that there has, for a variable that's frozen to either plus or minus, there has to be some clause that forces it to take that value. So here the vertex v is a plus, and it's forced to be a plus because within this clause there's 2 minuses. So if it's not a plus, then and none of the edges are negated. So if it wasn't a plus, then the clause would be violated. So the only option you have for v here is a plus. And so we say that this clause, in this clause, v is forced to be a plus. On the other hand, for a free variable, it has to be able to take both values, so it can never be forced. So if the clause looked like this, well, because there's a plus here, this clause will already be satisfied, so it's not forcing this the vertex u to be one value or the other. Okay, so that gives you a new spin system with this new set of rules, but we can go through the same kind of procedure. Say, what is the and some vertices will have different probabilities of being plus and minus and free. So there'll be a different set of marginals. Like a completely isolated vertex will just always be free. And for instance, and it turns out just by some of the symmetries of the model, it's enough to keep track of just the marginals that a vertex is a plus. And by symmetry, that will be the same empirical distribution as the marginal that it's a minus. Okay. And so if you go through the same sort of idea of saying, what happens if you add in a new variable, that shouldn't change the empirical distribution. So some fixed point must be satisfied. Well, this is the fixed point equation that's satisfied, and it's, you know, it looks very similar. The only difference is the formula here is a little bit different, which is essentially because it's saying that the only difference is that you can't, a variable is not allowed to be both plus and minus. If it can be both plus and minus, then it should be free. Okay, and so then the prediction is, again, okay, you look at how the partition function changes if you of this new plus minus 3 model, how that changes if you add in a new variable and you remove some clauses, and so this is the guess of the exponential rate of growth of the number of clusters, and the theorem is that this gives the right prediction, at least for large enough values of k. So it's the largest root of this of phi, and so it's essentially the point at which you expect the number of clusters to go from growing exponentially to being exponentially small. So one thing you could ask is, well, why do we need this to be k large enough? Well, there's lots of reasons, but one of them is, okay, you can actually look at what this measure nu looks like. This is, and remember it encodes sort of, for a randomly chosen vertex, what is the probability that it's a plus? When k is big, the distribution you get will be very nicely concentrated around a half. I mean, it'll have a non-trivial distribution, but it will be pretty well approximated by a point mass at a half. On the other, and if you simulate it, even for k equals 4, it still looks sort of nice, has a nice sort of peak around a half. At k equals 3, where the prediction is still supposed to hold, it doesn't look concentrated at all. It looks like a very spread out sort of a measure. So if you wanted to get really down to the right threshold, you'd have to deal with sort of measures that you can no longer, you know, hope to approximate by just saying that they're, you know, reasonably close to a point mass. Okay, so to count the clusters, we can give a sort of different encoding of them, which was developed by Kodjoglou and Panagiotou, and this is a way of labeling the sort of the edges of the graph, the ones that connect the variables to the clauses, as one of 4 colors. So there'll be, if the edge is satisfied and is a forcing one, then we'll color that red. If it's not forcing but satisfying, we'll color it blue. If the variable is free, we'll color it green, and if it's sort of unsatisfied, we'll color it yellow. So for a clause, for an edge to be forcing, it means that all of the other edges have to be unsatisfied. Otherwise, you know, otherwise you could, you know, the clause would already be satisfied, and it wouldn't, you know, it wouldn't be forcing. So if you have a red, you can only have one red edge in a clause, and if you do, all the other clauses have to be yellow. Alternatively, the clause has to have at least 2 edges that are either blue or green, and those are basically the set of rules for what clauses have to follow. The variables have to either be all green or have at least one red edge, and you can't have a red edge that forces it to be both a plus and a minus. So those are the sort of rules that this coloring of the edges has to follow, and it's equivalent to this model of labeling variables as plus and minus and free. okay, so we want to count these, and now we need to deal with the fact that different vertices will have different probabilities for, and so we'll define sort of vertex types, which will just mean, so we have our graph, you have a vertex, and you just look at a ball of radius r. And so r you can think of as some large constant, which we're ultimately going to take to infinity, but for now just think of it as some big fixed number. So the vertex, its type is just the graph inside this big ball, which will almost always be a tree. And so it should remember the tree structure plus which of the edges are negated or not. Okay, and then for the clause type will just be the vertex type of all the variables in that clause. Okay. Now, if I tell you the vertex type, you could sort of approximately work out what the marginal probabilities should be on these edges. And one way of doing that is by setting some sort of reasonable boundary condition on the boundary, essentially just that plus and minus are equally likely, and then working out what the marginal probabilities are at the edges incident to the vertex. And so we'll call that pi e. So for any sort of edge between a variable and a clause, it'll have some marginal probability over the four possibilities of blue, yellow, red, and green. Okay. So we're going to condition on the number of different vertex types and clause types we have, but only after we've sort of deleted some really bad vertices. So the variable with the most that's in the most number of clauses will be in log n over log n number of clauses. It's like the maximum of a Poisson random variable. So we want to get rid of the really bad, the really high degree ones, and actually there'll be a whole list of bad things that we want to get rid of from the graph. But we can't just delete like a big fraction of the variables, because that's going to change the threshold. So what we need to do is we'll delete a fraction of variables epsilon r that's going to be tending to 0 as r goes to infinity. And and I'll tell you a little bit more about this process later on, but basically we look at the graph, look at the worst parts of it, get rid of them, and in such a way that the graph that we're left with is uniform given the vertex and clause types of what's left. Okay, and then we want to count the number of these clusters on the remaining graph, but in a particular way. So we want to say that for each clause type, so you have a clause, and it knows the types of each of the variables in it. And you could say, okay, we'll look at all the clauses of this clause type in the problem, and then look at on all of the edges that correspond to this edge, what fraction of them are blue, red, yellow, and green. So look at the empirical distribution of that. And what we're going to do is force that to be this pi of e, the one that we approximated from the local neighborhood. So this is kind of a convoluted, and Okay, and solutions that satisfy this for every edge and clause type we'll call judicious solutions. The reason for this convoluted definition is that this is a choice of putting a spin system on the random graph that doesn't tilt the random graph, like doesn't change the structure of the random graph. It doesn't make some graphs more likely than others and change the distribution. And that's so in particular it won't mess up the second moment method. And really defining it in this way is sort of is crucial. Okay, so then you can say, okay, well, how many judicious solutions are there? And the first moment is actually pretty easy. You don't really need to do an optimization step because we've really specified most of the empirical distribution as part of the definition. So you can just write down what the exponent is, and it's going to be approximately close to the prediction minus some error that will go to 0 as r tends to infinity. So so if alpha is slightly smaller than the predicted threshold, we could take some r big enough so that this would still be positive. Okay. Okay. So then we want to do the second moment method, and so we're counting pairs of these clusters or colorings of the edges, and we want to show that the biggest contribution comes from the product measure. Now, some just some straightforward calculations and bounds will say that most of the pairs are either basically identical or basically independent, and the ones that are basically identical are sort of easier to deal with. So most of the challenge is with pairs of solutions whose distributions look fairly close to being independent. And so we want to show that the optimum really comes from pairs whose empirical distribution is really the product distribution. And so I've been saying that the marginals on variables change for different vertices, vary for different vertices. They depend on the local neighborhood. Although the approximation you get becomes very good as you increase the radius. It converges very quickly. But for most vertices, the number of neighbors they have is going to be very concentrated. I mean, the degrees that we're talking about are about 2 to the k. So the probability that the degree is, far away from that will be doubly exponentially small in k. So when k is big, everything is very concentrated, and most variables will, or most of the edges will be equally likely to be blue or yellow, which means sort of they're not a forcing edge, and they're equally likely to be satisfied and unsatisfied. There's only a small chance that they're a free variable, 2 to the minus k, and only also 2 to the minus k minus 1 chance of being red. So this is sort of approximately equal to, and this will hold for all but a doubly exponentially small in k fraction of the variables. Okay, so suppose that this happened, that this were true for actually all of the different vertex types. It's not, but suppose it was. Then how would we do this optimization? We can do a sort of again, like we did yesterday, a sort of resampling procedure. We choose a pair of solutions according to the optimal empirical distribution, and suppose it's not the product measure, it's say And then there'll be some vertex type t, which is, in a sense, the furthest from being a product measure in some metric. And let's say that it's sort of delta far being from some metric. So we just take all the vertices of type t in the graph, and then what we're going to do is delete all their clauses and then resample the clauses and the states, conditional on the solution being judicious, and see what the distribution we get after that resampling is. And it turns out you can show that after you do the resampling, the distribution you get at the root will be a distance at most delta times d times 4 to the minus k from the product measure in some metric. So what it says is and d is about 2 to the k, so this will be much smaller than delta. But if this were the optimal empirical distribution and you did resampling, you should get the same thing back. Otherwise it wouldn't be the one that gave you the biggest contribution. This should, if you start from the, because if you start from a uniformly sampled solution, it should have empirical distribution h. Then when you resample, it should still have empirical distribution h. You'll have an exchangeable pair. So you shouldn't change the empirical distribution when you do this procedure. But if it's far from the product or if it's not the product measure, it will change. Okay, so this would work well if all of the vertices were typical. Okay, but there will be some vertices in the graph that are, let's say, have degree bigger than 4 to the k. And so this procedure wouldn't work with them. And we can't just delete those very rare vertices, because doing so would shift the threshold a little bit. So we can't afford to do that. So we have to deal with the atypical vertices, and essentially what we do is, say when we have a very high degree vertex, we're going to say, well, most of the time we can surround it by, that it's surrounded by layers of more typical normal looking variables. So whenever we have a sort of really bad looking variable, we'll surround it by sort of nice looking variables, and sort of, we call this a compound vertex type, where we just say, okay, well, this is like one big complicated variable that includes, a collection of variables around the really bad one. And so the argument is to define these sort of compound vertex types in such a way that so you have a vertex, maybe now with really high degree, and we sort of look at some bigger window around it. So such that, okay, this is very high degree and looks sort of unusual, but sort of in most of this enclosure, the variables are just sort of the average case looking variables. Okay, and so, and we we could consider this whole structure as just a single variable with a sort of more complicated set of values that it can take. And then what we want to do is take these compound vertex types and just do the resampling of all of those. And so now the boundary is much bigger, but all of them are far from the sort of really bad part, and well, there's you can show that in some sense there's a when you do this resampling, there's some sort of a entropic decay of correlation argument that says that when you do the resampling, the distance from the product measure will again decrease. Okay, but we can't make these enclosures too big. So, and sometimes sometimes in the graph you could find just a really long string of high degree vertices. And if that happens, then those ones we're just going to completely delete. And how big that has to be, that will be some function of r. There are other things that can go wrong. We prescribed these marginal distributions on the edges, but when we calculated them, we calculated it by taking a variable and looking at a radius r around it and estimating the marginal for that. But different, the balls of radius r around different variables are not the same. So they can be inconsistent. So you could have a clause where things could go wrong. For instance, you have some clause. Each edge here has some probability of being a red edge, and it could be that they add up to something bigger than 1. But we said that clauses can only have at most one red edge, so that would be inconsistent. So when this happens, then we also just delete those clauses. And then, okay, sometimes clauses or sometimes variables are near lots of things that have been deleted. So we'll delete those ones too in like a bootstrap percolation kind of an argument. Because if you deleted too many variables in a neighborhood of a variable, it could change the distribution too much, and you wouldn't it could be bad. So we okay, so we have this okay, and then there are several more pathological things that can happen. We delete them too. And the full definition of the things that we exterminate from the graph is a few pages long. So I won't tell you all the details of that. But the point is that what counts as bad enough that we should delete it changes as a function of the radii that we're looking at around balls. And it has to be that the total number of vertices that we get rid of gets smaller and smaller as we look at bigger and bigger radii. And so that's okay. So that's crucial. And so for each value of r, the second moment method will hold up to some point that's slightly below the critical threshold, and we show that as the radii that we look at grow, then the difference tends to 0. And so Freegutt's result that there's a sharp threshold for SAT says that okay. And the second moment method will just say that there's some positive probability now that we have a solution, and probably as a function of r, this positive probability will get really tiny. But Freegutt's result says that if at some density you have a positive probability of having a solution, then if you just look at anything slightly smaller, then the probability of having a solution will tend to 1, because that probability has a sharp threshold. Okay, so this altogether gives a sequence of lower bounds which converge to the right 1 RSB lower bound, and the upper bound can be proved using a version of the interpolation argument that I talked about yesterday. So essentially, you just the interpolation method gives an upper bound on the threshold in terms of taking some infimum over some measures, and if you know the sort of right predictions to make, you know what measure to plug into the infimum, and you get a bound, and it's the right bound. I should say, well, okay. The interpolation method doesn't work with random k-sat. You have to do it at finite temperature, so this sort of e to the minus beta, the number of solutions. But you get a bound for each sort of beta, and then take beta to infinity, and you get the right upper bound. Okay, thanks for listening.
Any questions?
Can you rephrase the open problem that you mentioned at some point?
There's lots of open problems. The sort of, the current status of things is that there's this sequence of phase transitions and predictions about where the transitions happen and what happens, in each of the phases, and for some of these models, or for some of these predictions, we can identify like a model in which we can prove it, or one or two. But for something like, there's lots of open, but like for the random coloring model, we don't know what the colorability threshold is for, in a sense, most of the questions are open problems, and then like for random k-sat, we don't know, we only know this for like a k which was so big that we didn't compute it, because that means tracking this like more quantitative estimates through dozens of lemmas, rather than just saying, well, for big enough k, this inequality obviously holds. And there's lots of points where you say, k to the 10 times e to the minus k over 10 should be small, but k has to be big enough for that to hold. But in principle, for random k-sat, this the second moment argument could just work all the way down to k equals 3, but things will be much less concentrated, and that's that would be very challenging. Yeah.
So is 1 RSB expected to hold all the way up to k equals 3?
Yes. Yeah. There are some predictions for k equals 3 which don't correspond to 1 RSB. Like if you're looking at sort of clusters of different ranges of sizes, but for just the satisfiability threshold, then even for k equals 3, and even the sort of heuristics underlining the proof ought to still be true. On the other hand, for the random independent sets, the 1 RSB threshold should only be true for d greater than or equal to 20, and for random regular graphs with d less than or equal to 19, I guess the prediction is that it's full RSB, or at least that it's not 1 RSB, and that the maximal independent set will be strictly smaller than what you'd predict from the 1 RSB formula. For colorings, I think it's that when you have, I think for 3 colorings it's full RSB, but for 4 or more it's 1 RSB. There's also, for random k-sat, there's some other things that change for low values of k, like there's a threshold where most of the messages of belief propagation are frozen in the sense that they're mainly either 0 or 1, and for large k that's always much smaller than the condensation threshold, but for small values of k it's bigger. So, but still smaller than the satisfiability threshold, so it shouldn't change the proving things around the satisfiability threshold. And then, I mean, a whole other sort of set of open problems is, you know, asking about what happens at finite temperature, where you have, you know, some of the clauses are allowed to be violated. And so, I don't know. So one thing I've been thinking about a lot over this summer is how many independent sets there are of sizes a little bit smaller than the maximal independent set. And if you do that, the complication is that rather than most of the messages being either 1 or 0, there's really a continuous distribution of values that the belief propagation messages can take. So sort of grappling with that.
So just in addition to what you were just describing about you know, getting k down to k-sat down to 3-sat, these other models, finite temperature, are there other things you would say are sort of the most exciting directions the field will go in the next 5 or 10 years? What do you see as the promising future for us to look toward?
So I mean, one so there are very simple and natural full RSB models. The simplest of which would be like the max cut model, so, or you can think of it as just like the ground state of the antiferromagnetic easing model. So you want to partition the vertices to have of a graph to have the most edges going between them. And so there's been some work on this in terms of if the degree is very large, sort of kind of coupling that with the Sharrington-Kirkpatrick model, and and that's gotten some sort of interesting bounds and some sort of like the first order approximations to the thresholds. But I guess the question of, is there some combinatorial way of understanding what's happening at higher levels of replica symmetry breaking, I think is maybe the most exciting question.
Okay, my next question is, if people in this room want to go read about this, what should they read first?
Okay, so
just overview of the lectures, you know, just
Yeah.
the general. If someone wants to dive in a little
so
bit.
Okay, it's sort of the higher level background. The first thing maybe is the book of Mazard and Montanari, which describes sort of some of the predictions, not the proofs. I'm in the middle of writing an expository paper, which and I have a deadline for that because there are these lectures at Harvard, I guess, where you're forced to write a 60-page expository paper for it. So at least by November, we don't at this point have a very good set of notes about the most recent stuff, and that's something I'm hopefully going to have soon.
Okay, thank you again, Allan, for this info.